So let's get started. So welcome back, everyone. So today we'll finish the review of linear algebra, talking about square matrices and stuff, and odds and ends. Quick reminder: quiz 2 is due today. Happening today. That means we'll end the lecture a bit early, around 10:35. Again, if I seem oblivious to the clock, please wave me off. So I recommend you take the quiz kind of during class, starting at 11:35. Yeah, so we'll end at 11:35. I recommend you take the quiz then in class. Me and Ian will be around in case you have any questions on the quiz. The same on Zoom. I will stay on Zoom to help answer any questions. We'll try and answer questions later in the day. You have until the end of the day to finish it, but the response might not be as quick. Once you start, you have half an hour to finish it. If you have not made your cheat sheet yet, you still have some time to do that. But remember to have that preloaded on your device you're going to take it with, because you upload that as part of the quiz, and you can earn 5 points back that way. Great. Also, homework 2 is coming up. That will be due next week on Tuesday. You still have some time to do that. That's not one I'm particularly worried about for all of you, but don't do it at the very last minute. There are extra office hours. So today at 1:30 on Zoom that we added for Thursday office hours. And then you can ask me after class, and then Monday and Friday I have office hours, and Monday and Tuesday there are a bunch of office hours. So great. And then after today, next week we get to start into linear regression. It's exciting. We're finally getting to the different sort of like actual analysis sort of techniques. This kind of concludes the kind of background third of the course that allows us to have the language and terminology to describe all of these algorithms and techniques. So we'll start being in these different sections: linear algebra, dimensional reduction, clustering, and classification. Each of them we'll kind of see what this analysis type is. We'll go through some simple, common, basic algorithm, and you'll understand the basics of all of those. And we'll be introducing other important concepts along the way. So great. So that's where we are in the schedule. And homework 3, we'll work on getting that out soon. That one will be a bit longer. Hopefully not too hard, but less review components than the previous homeworks. Okay. All right, so let's try and get through the rest of the linear algebra material before we have to break for the quiz. All right, the first thing that we're supposed to cover on Tuesday we didn't get to is the rank of a matrix. Right. So you're going to find this for a set of vectors. If we have a set of vectors x1 up to xn, and these are each, say, in Rd, right? So then the rank is the size of the largest subset, x prime, a subset of x. So subset of the vectors that are linearly independent. Okay, so on Tuesday we talked about this term, linearly independent, right? So this meant that if they were linearly dependent, the vectors were linearly dependent, I could write one of them using a a sum of scaled copies of the other ones, right? If they're going to be linearly independent, it means I can't do that. It means there's more, every vector allows me more things I can represent. And you can think of it as adding like a dimension to the space you're dealing with. Every vector kind of goes off into to a new dimension. Okay, this is not like Marvel Universe where you're, different parts of the timeline dimension, but kind of these, so geometric dimensions. Again, if you think like we have, some vector, say V1 here, I have another vector V2, and I've drawn them on the tablet here, and you see them on your board or your screen, and you see them, they are occupying a two-dimensional space, right? They're this two-dimensional space of this board, but you can imagine that another one is coming out of the plane. This one would be linearly independent of those. I can't represent it. Anything I can represent as a scale copy. Remember, I had this equation z equals sum I equals 1 to say k of alpha I times xi, where this alpha I is a scalar value that I can scale them by. It can be negative. I can use this with where v1 and v2 are like, I can, instead of xi, I can make these as, say, x2 and x1 here, right? Then I can write anything in the plane, anything on the board as some, by choosing the alphas correctly, as kind of some combination of those. But I can't do something that's coming out of the board. That would be linearly independent. So if I added another vector here, let's call this x3. This is also on the board, so it's not adding to the kind of the dimensionality that these vectors can represent. So with these vectors, the rank would be 2. So this is an example of rank of this set equals 2. Any subset I take of them will still only leave me in the board. Okay. All right. So you can define it for a rank for a set of these vectors, right? You can define a rank for a set of vectors, but it's more commonly to be used the rank of a matrix. So rank of a matrix, say A in R and D, right? And a matrix, remember, we can think of this A is just this set of these up to AN. You can think of this as the set of these rows. Each of these rows is a vector. Well, then I can define the rank based on these rows also, right? So I can take these row vectors, there are n of them. Maybe my x1, x2, and x3 are row vectors in a matrix. Well, then I can describe the rank of the matrix in the same way, right? It's the rank of those rows. There's another way of thinking about matrix, which as a set of these columns, and usually I'll use uppercase A1 through AD, and these are now column vectors the same way. And I can also think of the rank of these column vectors, okay, as the column vectors, right? And then these are also give me a set of vectors, and I can define the rank. The answer is always the same, okay? No matter whether I define it by the set of column vectors or the set of row vectors, the maximum subset, which is linearly independent, is always going to give you the same answer. Okay, so it's always going to be the rank of the matrix is the rank of the rows or of the columns, and it's always equal the same, right? So it's always the same whichever one of those I choose. All right. So I often say, if I have a matrix, A in R n cross D. So I know because of this property, that the rank of A is going to be less than or equal to the min of N and D, right? So this is the min upper. Remember, we talked about the arg max and the arg min. That was returning one of the things in the set here. Yeah, this is doing kind of the same thing. I'm returning either N or D, whichever is smaller, and that upper bounds the rank, right? Because it's the same, I get the same answer whether I take the rank of the rows or the columns. Then it can't be larger than the number of rows or the number of columns. Okay, and if rank of A is equal to the min of N and D, the set, then I'm going to say this is what's called full rank. Okay, so this is what's called so full rank. So I could have like 1,000 rows, and each of the rows has so 3 values, right? There are 3 columns. If the rank of the matrix is 3, right, then this is full rank, even though it's much less than the number of rows, right? It's based on the minimum of the values N and D here. Okay, and so we'll often be dealing with, starting with full rank matrices. We'll be storing data sets representing them as matrices, and it's quite common to assume, because there's noise in the process, every element has a little bit of noise to it, that it's going to be unusual if they happen to lie in exactly in a lower dimensional subspace, that I could not make them full rank. So typically our data is going to be stored in matrices, and these are going to be these full rank sort matrices. We'll talk about techniques that inside of an algorithm, you might make another matrix that's a lower rank one. You might construct that in an algorithm, but usually as input, we'll assume the input is going to be full rank. Okay, so that means every kind of new data point I add is somehow, can't be perfectly aligned with the other ones. I can't get this equation here. Remember this key equation right here. This has to be exactly aligned based on the other ones. And if it's not just exactly kind of represented in the span of the other matrices, this doesn't count. Okay, and we'll talk about how to think about and deal with this noise later on this semester. Okay. Okay, great. So that's rank. Let's move on to kind of we're going to talk now about some properties of square matrices. Okay. So it's a square matrix, right? This would be a matrix A, right? It's in R n by n. Okay, so the point of a square matrix is the same number of rows and columns. Okay, so when I look here, n is the same as n, right? Those are the same value, right? And if I draw it in this rectangular form, it's going to be think of exactly as a square. It's the same number of rows and columns, right? You think of it as a square in some sense, hence the name. Okay, and so there are a bunch of nice properties we get from, or they're nice properties you can assign to square matrices that makes them easier to deal with and work with. Square matrices will usually not be a direct representation of data the same way that the more general set matrices. Typically, if we represent data, it's not going to have the same number of rows and columns. That would be an accident if that happened, or maybe not a very good situation in some cases. Whereas square matrices, we will see these a lot in the semester. These will typically be constructed at some like intermediate step of an algorithm. Okay, and the square, because they're constructed in a certain way, they're often going to have certain properties to them because of how they were constructed. Okay, and so we'll kind of talk about some of the nice properties they can have, and I'll say, yeah, usually when we deal with square matrices, they will have these properties. Okay. Okay. So the first one to talk about is the inverse. Okay. The inverse is a kind of a pretty important operation, and may have, if you were from the lecture last week on Thursday, you may have been kind of in the back of your head thinking about how we do an operation, and the inverse is probably that. Okay, the inverse of a matrix, and you can only define this for a square matrix. Okay, the inverse is often written as to the power -1. Okay, we take a matrix to the power, so -1. Okay, so, okay, and it has, the inverse has the property, so it, such that A inverse times A is equal to the identity matrix, and similarly, A times A inverse, right? So the identity matrix is a diagonal matrix that has all ones on the diagonal elements. So the kind of yeah, so on the diagonal elements are all 1, and off diagonals are all 0s. And typically you would write it in this way. So this would be all 0s here. So it's pretty simple to represent matrix. And this is in general, this is an element of our n by n also. This is also an n by n matrix. Okay, and so I get this by multiplying A by A inverse, or A inverse by A. Remember, in multiplication of matrices, the order you do it can be important. In this case, it can go either way, so it's not as important in this case. But I can do that. I can multiply a matrix by an inverse of itself, because the inverse is also going to be, I'm also going to have A inverse is also going to be in a square matrix, is also an n by n matrix. Right, so it's an operation that turns a matrix into another n by n matrix, and then I can multiply them together because some of the n's match in the right place, and I can do it in either order because they're both n by n. Okay, and it's defined such that it gives me this property that I get back the identity matrix. Okay, so this, you know, hopefully you've kind of seen this before, but this may not kind of make a lot of sense what this means. If I instead think about a scalar value, right? So a real value, right? So if I have a real value, let's say it's like, you know, 7 or something. Well, then if I do a alpha to the -1, what is this doing? It's the -1 is actually taking it to the first power, but the minus is making sure I'm dividing. So I'm doing 1 over alpha. Okay, and if I put that next to, and if I do alpha times 1 over alpha, right? Well, what does this do? Well, the alphas, you know, good. The alphas here cancel. And so what I get back is 1, right? So I'm getting back 1 here, right? This is the property. So it's something I can multiply by a matrix A, so I get the identity matrix. The identity matrix plays the role of 1, and the inverse plays the role of, so division, right? So this is, so we talked about addition. And addition, actually, by putting a negative number in front, gave you subtraction. So we did addition and subtraction. We did multiplication, matrix multiplication, but we didn't talk about matrix, so division. Matrix division is done by multiplying by the inverse. Okay, and it's defined this way because for not all matrices can you actually divide by them. Can you take the inverse? The inverse is not always defined. I cannot always, for not every matrix A, can I find another matrix A inverse so that if I multiply them, I get back the identity. Okay, so so sometimes there's things called like the pseudo inverse, and we're not gonna get so much into that in class. Okay, so for a matrix to be invertible, okay, I must have certain properties. It's invertible if I can take the inverse. So that this means that A has to be square. So I can only invert it if it's square. Otherwise, these dimensions aren't going to match, aren't going to line up. It has to also be full rank. Okay, and it has to be full rank. So if I have these two properties, so that means the rank has to be n, right? So that the rank of A has to be equal to exactly n, and it has to be square. If these two properties hold, then I can take the inverse. That may not always hold, but in general, this is for matrices we will see in class, this will hold if we construct them in the right way, square matrices in the right way. Okay, and then we'll be able to invert, we'll be able to take a division, and this, as you can imagine, this might be important. Okay. Okay, the next kind of another important property about square matrices is eigen vectors and eigenvalues. Okay, so I'm just going to define these today. I'm not going to give as much intuition about them because we're going to spend more time getting to them later in class through another kind of notion called the singular values and vectors. Okay, but these are the vector. This is an eigen vector and a corresponding eigenvalue. Okay, these satisfy for a square matrix M in R n by n. Okay, so now I'm going to have that this guy is in Rn. V is an n-dimensional vector, and this is R. So lambda is a scalar. So these satisfy this property, which I'm going to write here. M times the vector. If I take my matrix, then an eigenvector satisfies that if I multiply it by the matrix, I get back the vector again. It's going to be scaled. It's scaled by lambda, okay? But I get back the same vector, okay? Okay, so you can see that, again, this requires M to be a square matrix because if M times V, it's going to give me back an n-dimensional vector again because it's square. Okay, if it was not square, it would give me back a different dimensional vector here. So if it's going to equal the same vector, a scaled version of it on the right-hand side, it's going to have to be a square matrix, okay? And so this fact that it gets back the same vector should be kind of weird. At first, you might think, okay, this is weird that it can actually happen, that I get back essentially the same vector. And then you think it's actually kind of cool, and that these vectors somehow are special. Okay, and these will be special in a certain way. They will describe kind of the eigenvectors that satisfy this are going to kind of describe some nice properties about kind of encapsulate a lot of information about the matrix M. I'm just going to define them now because you probably saw eigenvector and eigenvalues in a linear algebra class. But it's not it's probably not assured that you saw the singular value decomposition. Hopefully you did at this point, but when I started teaching this class, I don't think it was regularly taught in. And so we're going to spend more time on that. And we're going to build intuition on that decomposition. And those relate very closely to these eigenvectors and values. Okay, but so it's the review part. So that's what I'm just reviewing here. Okay, so if if M is full rank, right? So if its rank is n, then it will have n eigen vector and value pairs. Okay, so then they're vector value pairs, right? I can always take an eigenvector and kind of scale it, so I can multiply it by 2, and then I can divide lambda by 2, and I get back kind of the same one. So often we'll have the convention such that these values are exactly equal to 1. The norm of them is 1. That kind of grounds it. It's not always a convention, but that's what we'll use in this class, which is pretty common. Okay. If the rank is lower, it'll have fewer eigenvectors and values. Okay. So the number of eigenvectors and values has to do with the rank. I think all of our square matrices will be full rank in this class, unless I give an example of one that's not full rank. But in general, the number of vec and value is going to be equal to the rank of M, right? So the number I'm going to get is going to be equal to the rank. Okay, and one strange thing about them is that the eigen values, these lambda values, these might be negative, and they might actually be complex. By complex, I mean that these might have like imaginary numbers. They might actually have a component which is imaginary. When you get something like this, it's kind of a mess to deal with. Luckily, in this class, and most of the day analysis, you often, if you do stuff correctly, you don't ever get imaginary values for your eigenvalues. Okay, they could be that, but we're gonna describe another condition next that's going to say when I have that condition, I don't have these properties, and then I can think about having positive eigenvalues, and these will actually kind of positive and real eigenvalues, and this will allow me to say some nice kind of think about them in nice ways. Yeah, I should write a note up here, or yeah. So these eigenvalues can actually be complex. They aren't just real values. Okay. Okay. So the next kind of more specific class of matrices are going to be what's called positive, so definite matrices. Okay, and these are square matrices M in R n cross n. Okay, and such that they have n real eigenvalues. Okay, so a positive definite matrix is a square matrix with n real and positive. Yeah, n real and positive eigenvalues. So all the eigenvalues are real and they're all so positive. And this kind of makes things nice, and these will be interpretable. and in certain ways we'll see later in the semester. And the ones for the square matrices we will construct will have this property or the next property. There's another alternative way to say this. For there's another alternative condition for any vector x in the n-dimensional real vectors. It satisfies that x transpose mx, this one has to be greater than 0. So if I took any matrix and I multiplied it by m on both sides, it's kind of like, when I multiply it on one side, right? If I think through this a second, if I do one multiplication, this is it's going to get back another n-dimensional vector. And then this x transpose that other vector is going to be kind of like a dot product. So it's going to get back a scalar value doing vector-vector multiplication with the matrix stuck in between. And so it's going to get back a scalar value. And this is saying for any matrix I do this with, the value has to be positive. Turns out these conditions mean exactly the same thing. These are exactly the same condition. This is encoded in all the real positive eigenvalues. Okay, and this is kind of a nice, turns out will be a very nice condition to have. Okay. Okay, and so, and there's a slightly weaker form we will sometimes encounter, a positive semi-definite matrix, okay, where I put the semi in front here, and that means that it will have n real eigenvalues, and they need to be positive or 0. Okay, so instead of positive, some of the eigenvalues can be 0. So they're not negative, but they can be 0. And it also satisfies this condition, for any x. Now, before I had greater than 0, now I'm going to add greater or equal to 0, right? So this is identical to the condition. If I took any vector x and I multiplied it on both sides by m, I'm going to get back a scalar value, and that scalar value has to be positive or it could be 0. Okay, so this kind of condition is actually, it's a pretty big difference. This kind of reduces this. This would be the case for non-full rank matrices. A positive definite matrix needs to be full rank. This one does not need to be so full rank. That's what's going on here. Okay, so these conditions will kind of make more sense when we talk about how we construct the square matrices, and we talk about the SVD later on, which will be a core part of the dimensionality reduction section class. Oh, okay. Let me just make this concrete. How are we doing on time? Let's do a really quick example. Let's have M is going to be a 3 by 3 matrix. 1, 3, 4. Stick to the example because I pre-computed stuff. 3, 5, 2. 4, 2, 8. Okay, so this is a square matrix. This is in our 3 by 3. 3 rows and 3 columns. It's a nice square matrix. Okay, so now I can write the first eigen vector. So this will be V1. It will often write the first one, and this one will, in our notation, will correspond with the largest eigenvalue. And so this will be 0.43, 0.44, and 0.78. I've rounded these to 2 digits. It's not exactly these values. This is the scaling. This should be a unit vector. So if I square each of the individual terms, they'll shrink. When you square something less than 1, it shrinks, and then I add them up, they should add to 1. Okay, you're like, how can those add to 1? They add to something greater than 1, but you square something less than 1, it shrinks. Okay, and lambda 1 is equal to 11.36. Okay, it turns out that the spectral norm of this matrix is actually equal to the squared spectrum. No, the spectral norm of this matrix is equal to the first eigenvalue, right? So this happens to be equal to the spectral norm of the matrix. That's kind of a cool. That's why it's spectral actually refers to the eigen decomposition sort of world. That's that connection is a little bit longer than I'll get into, but that's why it's called the spectral norm. Okay, and so that kind of tells us how big the matrix is in some sense. And I can write down the other eigenvectors and values. V2 is minus 0.11, minus 0.83, 0.54. The fact that there are negative values in here doesn't matter, in fact. These vectors, the direction of them doesn't matter. I could flip all the signs on the vector, and it would still be the same eigenvector. And then the second eigenvalue is 4.10, and V3 is equal to 0.90, 0.31, 0.31. Okay, and the third eigenvalue is going to be negative 0.46. Okay, so these are just kind of, yeah.
So in general, the square matrix is the largest eigenvalue.
Yes.
How about for the non-square matrix?
Yeah, then we'll define that later through the singular value decomposition later in class. But there's, yeah, so you can, turns out you can multiply a square matrix by its transpose, a non-square matrix by its transpose. That's always allowed. The result will give you a square matrix.
Okay.
And then that result is going to be and then the largest eigenvalue of that matrix, the square root of that will be the spectral norm of the original matrix. Okay. Okay, great. So I just want to look at this example. The direction, the sign of the vectors doesn't matter. The order of the eigenvalues is usually going to be important, and they can be negative here. So this means this matrix is not positive definite. It's not positive definite because this is negative. Okay, so this means it's not positive definite. Okay, because the last eigenvalue is negative here. Okay, yeah, questions in the chat? Yeah, so that, yep, the scalar value. Yeah, good. So we will, yeah, there's more. And if you look at if you're interested in that stuff, look at chapter 4 under the Mahalanobis distance. There's some cool kind of connections to look at this form here. Okay. Okay, so let me talk about another important quantity. We'll just define this quickly. Determinant of a matrix. I'm probably not even define this out. This is often defined for a square matrix, so that's why it's in this section. A, right, in R n by n, and the determinant is written this way, with single bars. Okay, so it's kind of important to use a norm, use those double bars instead, because a single bar, it's kind of like absolute value sort of signs, that gives you the determinant instead, which is not the norm. It's also a notion of scale of the matrix, but it's kind of weird. Let me try and define it compactly, just write it up here, is is A, so this will be an element of our n minus 1 times n minus 1. And this is A minus the ith row and the jth column. So I've taken A and I've taken out the ith row and the jth column. And then the determinant of A is going to be equal to the sum over I equals 1, n minus 1, I plus 1, A1I times the determinant. It's going to get back to scalar quantity, A1 comma I, yeah, like this. Okay, so this is the determinant. I'm only mentioning here because we will use this to define like a higher dimensional Gaussian distribution. The normalizing term includes this. So if you haven't seen it before, it's here. There's some couple more details in the book, but I would just think of it as some scale quantity that's not the same as the norm and only applied for square matrices. I'm not gonna dwell on that too much. Okay, we have one more 10 minutes to cover one more really important topic. And hopefully we'll get to jump to Python for a couple minutes right before the quiz. Okay. Okay, the last topic we're going to cover for the linear algebra review is about orthogonality. This turns out to be another thing that's very important. That's why we're covering it. So let's see. So consider two vectors, x and y in Rd. So I have two d-dimensional vectors here, and they're orthogonal if their dot product is 0. So they're orthogonal if x, y is exactly 0. Okay, so that's definition of orthogonal. How to think about this is you're going to have, some domain. I'm going to have two vectors. Let's call this one x. We'll call this one y, right? And I can think of these as vectors from the origin. Okay, and they're going to be orthogonal if this is a right angle, exactly a right angle, right? So, okay, so and this right angle and this picture I've drawn up here, like these can be much higher dimensional vectors, but this picture of them, thinking about them in a two-dimensional space and them being orthogonal to each other is something that is going to be true in the higher dimensional space also. I can think about whatever dimensional space that these vectors are in, right? I can rotate it around, whatever, but there is some two-dimensional space that goes through those two vectors and the origin. And in that space, you can draw the right angle, okay? So this picture makes sense. Even if they live in higher dimensional space, you can always find a two-dimensional one that they live in. This is the span of x and y, in fact. And in that space, they're going to have this nice right angle property, which is something you can define in 2D. There's some stuff in the chat. Are there? Okay, great. Okay, so this is orthogonal vectors mean. Okay, and remember the dot, question.
Would it still be orthogonal if x was like halfway up?
If x was halfway up to it.
Like it was split up, like the base of x was split halfway.
Oh. Okay, yeah, so let's draw a picture like if x was this vector here.
Yeah.
Yeah, okay, so this vector, so when I describe a point, right, when I describe x, this one's going to have coordinates, and let's say these coordinates are going to be like 4, 1. Okay, that describes I'm 4 this direction and 1 this direction, right? And that implies distance from the origin. Okay, if I have this other point up here, x prime, well, this is a point, and this is well, this might be 3, 5, right? Well, that the vector that point implies is actually this vector. It's not this one which is orthogonal, right? Okay, so if I have that vector, maybe I'm doing this x prime minus this other point. Let's call this p. If I look at x prime minus p, well, that gives me this vector, and that vector would actually be here, right? If I do x minus p, where p is that projected point, right? So if I do have that vector, well, it's actually a different vector through the origin. Yeah. Good. Okay. And so again, great. This is related to the point I was going to bring up, that if we think again about the dot product, remember the property that the dot product, if one of the vectors is of a unit length, and I project the other one onto it, it's the length of that projection, right? If I projected x, this original x, onto y, assume y is a unit length. Well, I project it onto y because it's orthogonal. This is going to wind up right there at the origin, and the length from the origin is 0, right? So it's important that when it projects onto this other space, it projects onto the origin. That means its length is 0 here. Okay. Turns out it doesn't matter that the scale of y is not unit vector. It will still, these things will actually cancel out, because if you remember the definition of the dot product, j equals 1 up to d, this would be of x, j, y, j, right? And if I multiplied all the y, make it twice as long, well, then all the coordinates for yj, all those individual coordinates, are also multiplied by 2, and that factors out, right? So if this is equal to 0, and I factor out a 2, it's still equal to 0. Okay, so we don't, for this to work, we don't need that unit vector for the projection to make sense. Okay, so we can do a small, okay, let me not do a small example here, but you can, to do this, if you want to know if two vectors are orthogonal, just calculate the dot product. Go and calculate the dot product. In high-dimensional space, it's harder to really know what's going on, but you can calculate the dot product and find out here. Okay, I need to say a couple more things really quickly. A matrix, okay, I can think about or I can think about a set. Actually, before I do this, let me say a set of vectors, u1 up to u, let's say k, are going to be orthonormal if each ui is a unit vector, and for all I and j not equal to each other, that ui uj is 0. So they're all orthogonal to each other, and they're all unit vectors. These are orthonormal vectors. Okay, and now a matrix with let's say a matrix u in R n cross n. Okay, so these should be a square matrix with all rows orthonormal and all columns orthonormal, then this is what's called orthogonal. Okay, an orthogonal matrix. It's a square matrix where all the rows and all the columns are going to be unit vectors. Okay, and they're all orthogonal with each other. Then the matrix is called orthogonal. This is a very special type of matrix. What it does is, and we'll talk about this much more when we talk about the SVD, but this will give us, it will kind of, when I multiply by it, any vector by it, it's still an n-dimensional matrix, vector. It's going to have the same norm. Okay, so I'm going to have the property that for for any x in Rn, that x times u, if I look at the spectral norm, that's exactly equal to x. So it does not change the norm. This should probably be transpose, or I can multiply it on either side. Multiply by either side has a property. It's not going to be, it's not going to change the norm. The other important property is u times u transpose is going to be the identity matrix. Okay, so this means that to take an inverse of an orthogonal matrix, I just have to do the transpose, right? I didn't describe how to take the inverse before. We will just see an algorithm later in the semester to take the inverse, and it's going to be a bit complicated and messy. It's often the bane of a lot of machine learning algorithms, taking the inverse. But for an orthogonal matrix, it's easy. I just do a transpose. So in fact, I just kind of change how I index it. And that's the inverse, and that makes it very easy to take the inverse in this way. And you can see that because it's, okay, so this is an identity matrix, and that comes right from the definition. The norm of UI, again, is UI dot UI, right? And this has to equal to 1. And this happens on the entries on the diagonal when I multiply the matrix by itself. I'm basically taking this dot product with each row or column by itself. And I have UI uj equals to 0. These are the off-diagonal entries in the product, and those are all 0. So this is why I get the identity matrix. Okay. So I went through this a little quick. Also, these vectors then form what's called a basis. Yeah, I talked about basis already, but it has the property that if I write x equals to alpha ui, I can write any vector x in this way in Rn. Any vector x can be written this way because the ui's form a basis, meaning they span all of Rn. But I have the property that the norm of x is equal to, these are alpha I squared. So basically, I can think of taking those alpha I values that I multiply the ui's by, and I string them together into a vector, and that vector's norm is the same as x. This is how I get this change of basis. And we'll see this allows me to do some really cool things. Okay, so this was pretty quick. If this was new, maybe refresh it, but we'll review this kind of in the context again, this stuff again in the context of singular value decomposition after fall break at some point. Okay, great. So the quiz should now be open, and you have until the end of the day to take it. Again, I suggest to take it now, but please don't talk now because some people may be starting the quiz. And I'll be around to answer questions for the next at least half an hour.
Yes,